Have you ever watched an athlete and just thought, how did they do that? It can honestly look like magic. But every single movement, whether it's a simple jog or a mind-bending flip, is actually following a hidden set of rules. We're about to pull back the curtain and look at the blueprint for how we move.
So, what is the secret? I mean, what could possibly connect a soccer player's kick, a gymnast's cartwheel, and a rower's stroke? On the surface, they look totally different, right? But believe it or not, there is a common thread that ties them all together. And that secret? Well, it's physics. Yep, plain and simple. All of these amazing athletic feats are governed by the exact same principles. So, we're going to break down that invisible science and make it totally visible, and hopefully, really easy to understand.
All right, first things first, we need to get our heads around the stage where all this action happens. I want you to imagine that your body is moving inside an invisible three-dimensional grid. This grid is made up of what we call planes and axes.
So here they are, the three main planes of movement. The easiest way to think about them is like invisible sheets of glass that slice right through your body, and they define the direction that you can move in. We've got the frontal, the sagittal, and the transverse plane. Let's take a look at each one.
Okay, so the frontal plane. This one slices your body vertically, separating the front half from the back half. So any movement that's sideways, think about doing a jumping jack or shuffling side to side, that's all happening right along this plane.
And a cartwheel is the absolute perfect example of this. It's pure frontal plane movement. See how the gymnast is moving completely sideways? It's almost like they're squeezed between two panes of glass, one in front and one behind them.
Next up is the sagittal plane. Now this one also cuts the body vertically, but this time it's splitting you into left and right sides. This is probably the one we use the most because it's where all our forward and backward movements happen.
For example, just running straight ahead, or like we see here, a long jump. The athlete is launching themselves directly forward. Their arms and legs are swinging forward and back, not out to the sides. That is classic sagittal plane motion.
And that brings us to our final plane, the transverse plane. This one's different. It's horizontal, and it divides the body into a top half and a bottom half. This is the plane of rotation. So anytime you twist or spin, you're using this plane.
The discus throw is just a brilliant showcase of this. A thrower gets all that incredible power from spinning their body. That massive rotation of their torso and hips, that is happening purely within the transverse plane.
Okay, so let's tie this all together. Each plane has an axis of rotation, basically an imaginary pivot point that the movement happens around, kind of like a wheel spinning on an axle. As you can see here, frontal plane movements, like our cartwheel, rotate around the sagittal axis. Sagittal movements, like a forward roll, rotate around the transverse axis. And transverse movements, like that discus spin, rotate around the vertical axis.
Okay, so we know where the movement happens. Now let's get into how it happens. Our body is just this incredible machine, right? It's a really complex system of levers that lets us generate force and get things moving.
You know, every single lever system, whether it's a simple seesaw or your own arm, has three key parts. You've got the fulcrum, which is the pivot point. In our bodies, that's our joints. Then there's the load, which is just the weight or resistance we're trying to move. And finally, the effort. That's the force our muscles apply to actually make it happen. Now, in biomechanics, these three parts get arranged in three different ways, and that gives us three classes of levers. Now, I know that sounds a little complicated, but I promise you there is a super simple trick to remember which is which.
And here is that secret. Just burn this phrase into your memory. Fly, little elf. Yeah, it sounds a bit silly, but this little guy is your key to mastering lever systems. Trust me.
So here's how it works. The first letter of each word tells you which part is in the middle for each class. Ready? F for fly means the fulcrum is in the middle for a first-class lever. L for little means the load is in the middle for a second-class lever. And E for elf means the effort is in the middle for a third-class lever. FLE, 1, 2, 3. It's that easy. Let's see it in action. In rowing, you've got a first-class lever. The pivot, or fulcrum, is in the middle. For a second-class lever, think of a long jumper pushing off the ground. Their body weight, the load, is in the middle. And for third class, a perfect example is kicking a football. The effort from the quad muscle is applied right in the middle, between the hip and the ball. So why do we even care how these levers are arranged? What's the big deal? Well, it all comes down to a crucial trade-off between power and speed. And this is where a concept called mechanical advantage comes into play. Mechanical advantage is really just a fancy term for efficiency. It tells us how much force multiplication we're getting out of a lever. We figure it out by dividing the length of the effort arm. That's the distance from the pivot to where the muscle attaches by the length of the resistance arm.
And this slide lays out that trade-off perfectly. When you have a high mechanical advantage, meaning a long effort arm, you are built for power. You can move heavy loads with less effort. On the flip side, a low mechanical advantage requires a lot more effort, but what you get in return is speed and a much greater range of motion.
So let's connect this back to our lever classes. This is the key takeaway. Second-class levers, remember, with the load in the middle, they always give you a mechanical advantage. They are our power levers. Third-class levers, with the effort in the middle, they always have a mechanical disadvantage. They are built for speed. First class can be either one, it just depends on where you put the fulcrum.
And this leads us to a really fascinating insight about, well, us. It turns out most of the levers in the human body are third class. Think about it. Kicking a ball, swinging a bat, a bicep curl. It means that we as humans are naturally designed for speed and range of motion, not for brute raw force.
So there you have it. From the invisible planes we move through to the tiny levers in our own limbs, the physics of sport is literally all around us and inside us. Now that you have the blueprint, what are you going to notice first the next time you watch a game or even just see someone running for the bus?